Jeff, a whole bunch of things. First, thank you for such kind words, and thank you for the invitation to be here. What an incredible place you have here. I mean, this is it's just outstanding, the sort of program that you have set up here. So, so I'm going to be telling you today. Funny thing, I'm going to be talking about weak values. What who would have thought that somebody would come to this meeting and talk about weak values? But with perhaps a slightly different slant on things, I'm going to talk about direct measurement of the quantum wave function. And well, if you're at 3 different universities, and if you're an overachiever, you can write 3 times as many papers. And yeah. So like Jeff, I was from MIT. We tend to be overachievers. Okay, so this is not the first time you have seen this yet today. This is the paper that started the whole thing off. Since the principal is not in the room, I've always felt that the title was just a little bit provocative, but perhaps not inappropriately so. But it sure gets your attention. And the point is that I will remind you that the standard expectation value in quantum mechanics is given by this formula, but that Aharonov and his co-workers introduced a weak value. And the question is, why are weak values important? Let's say I didn't write this for you. Right? This is my general talk about weak values. Well, they can lead to the amplification of weak signals. And in addition, they can lead to the direct measurement of the quantum wave function. Now, like maybe everybody in this room, I am a great fan of perhaps Professor Aharonov. And so I cannot claim to be at the level of the people that John Howell quoted, who have published 30 or 40 papers on weak values. But considering that I have a very broad set of research interests, writing 6 papers on weak values is not so shabby, I would claim. So I'm part of the family, so to speak. As we were told before, as we've seen this one before too, the very first experimental demonstration of weak values was Ritchie in the group of Randy Hewlett. Let's just remember what they did here. They had a linear polarizer. They had a weak birefringent plate, as we remember from our undergraduate education. When a beam of light goes through an goes through a birefringent plate, it splits into 2 components. I stuttered because I just said that once in the past 3 months, to my graduate students. Not a single one of them had actually seen that effect with their own eyes. So I went out and ordered some calcite plates so that they can actually see it in their own eyes. You know, students these days think that you do physics by sitting at a computer terminal and program the computer to see these effects. Oh yeah, I can program my computer to see a beam of light split into 2 components in going through a calcite plate. But the idea is that the beam breaks up into 2 components. You then use a linear polarizer set almost perpendicular to the first linear polarizer, and that gives you a much larger enhancement of the effect. So, of course, if there was no birefringence, you just get out the Gaussian that you put in. If you had a very strong amount of birefringence, the beam would split into 2 components. But the idea of weak values is you have weak birefringence. It does not split into 2 values, but the peak of this moves over. Under the conditions of this experiment, the birefringence would separate the beams by 0.64 microns, but the Gaussian is displaced by about 12 microns. So in this very first example of Randy Hewlett's group, they got a factor of 20 weak value amplification. Now, who comes on the scene but John Howell and Andrew Jordan? I will put words in their mouths. They said, if a bunch of Texans can get a factor of 20 enhancement, in Rochester we can get at least a factor of 10 to the 9th enhancement. So we're going to go after it. This was humorously provocative because Andrew is actually from Texas. He's from Texas, but I said, yeah, well, anybody can get a factor of 20, but a factor of 1 billion, that's something worth going after. And well, you've heard about this before several times at this meeting today, and I will not try to explain it to you, in part because I could not. It is, I mean, you get a headache when you try to figure out that there's beams going around this way and beams going around this way. But you know, they got femtoradians of resolution, femtoradians of resolution, and femtometers of displacement resolution. So but what I became interested in this in a slightly different context, and that was the direct measurement of the quantum wave function. Now, Jeff Lundeen is one of the new assistant professors at the University of Ottawa. Jeff mentioned that when I went to Ottawa, I was told I could hire 3 assistant professors to work with me. It seemed that at least one of them had to be a weak values person, right? Just putting what's important in front of things. So Jeff Lundeen is one of our new assistant professors, and he developed a method for the direct measurement of the wave function using weak values. So let me just talk you through what to me is the logic of this. So the wave function in quantum mechanics is notoriously difficult to measure. And one reason is that if you measure the wave function at any one point on the function, the wave function collapses. So you can't measure the entire wave function in a single measurement. You have to do it over and over and over again. And in a sense, this is related to the Heisenberg uncertainty principle that, well, you can think of the real part of the wave function as being position, and the imaginary part as being related to the momentum. So once you have collapsed the real part of the wave function, then you can't get the imaginary part. So historically, the wave function has been measured only indirectly and inefficiently using quantum state tomography. But this recent work of Jeff Lundeen showed how to measure the wave function directly. By directly, I mean that what comes out of the experimental apparatus is the wave function to within a multiplicative constant. You do not have to do a lot of post-processing, which is what you do have to do when you are doing tomography. And the trick, I'm preaching to the choir, the trick is that you perform a weak measurement on one variable, which thus only minimally disturbs the system, followed by a strong measurement on the complementary variable. So this is Jeff Lundeen's original paper on the subject. And, okay, so he starts off with the definition of the weak value of a measurement of the operator A. And then he says, let's say that we want to make a measurement of the position of the operator. So this is the projection operator XX. Make a weak measurement of position followed by a strong measurement of the momentum. So in this case, the weak value is the original wave function, well, the state vector projected onto X, X projected onto P, and then P projected onto psi. So this is just the momentum space wave function. This is the real space wave function. This e to the IPX. Well, if you choose P equals 0, this just becomes 1. And you see that's within a multiplicative constant. which you can think of as a normalization constant. This just directly gives the wave function. So here's how they did the measurement. They have a laser beam. And they intentionally, so they claim, intentionally they had a very bad laser beam. Because if it's a Gaussian, how would you know you've done anything? All laser beams are supposed to be Gaussians. So they took a distorted laser beam. They take a half-wave plate, very tiny half-wave plate. They translate it across the transverse profile of the beam. That makes a weak measurement by rotating the polarization by a small amount. Then they they project onto, with a Fourier transform lens, they look at P equals 0, P transverse equals 0. Using polarizing beam splitters, they measure the orthogonal polarization components of the polarization. That is the strong measurement. And here's the real and the imaginary part of the wave function. Or here is the intensity distribution, and here's the phase distribution of their wave function. So that's what they did. But now, even though we are very impressed with what they did, we should ask ourselves, but what is it that they did? And there has been, going back, at least throughout my entire career as a physicist, some debate as to whether it is proper to talk about the wave function of the photon. And people get very, very upset about this, call each other fools and idiots if they don't agree with exactly the other person, if the other person doesn't agree with their own interpretation. Some people think it's not proper to say it. I personally try to avoid using the word wave function of the photon because to me, a photon is one unit of excitation of a mode of the electromagnetic field. And I would prefer to distinguish the photon from the mode in which it lives. I like to think that Robert Boyd is one person, Robert Boyd's house is a different entity, and it would not make sense to confuse one with the other. Lundin, if nothing else, is clever. By the way, he's clever, and he was a student of Ephraim. Lundin hedged his bets. He called it the wave function of the photon, but he comments that some people call it the spatial mode of the photon. And here are some other people who have expressed strong feelings about this concept of whether it's appropriate to talk about the wave function of the photon. Okay, so let me tell you about some of the work now in my own group. This was a background. In my own group, we made the first direct measurement of the state of polarization of the photon. And of course, the polarization of the photon is an example of a qubit. And the qubit is sort of the fundamental carrier of information in quantum information science. So you'd think that being able to make a reliable measurement of a qubit would be something that would be very important for quantum information. And then then to show that this is extensible, we then measured the state vector of a state in a 27-dimensional Hilbert space. But let me tell the stories one at a time. So this is the measurement of the polarization state, of a photon. So this is the most general expression for the polarization of a photon. H is horizontal polarization, V is vertical polarization, alpha and beta are complex numbers. So I'll first tell you what we did and then tell you how we did it. So we can, using traditional polarizing optics, we can form whatever state we want. Then we go and measure it and make sure that what we measure is what we knew that we had formed. So we take two paths on the Poincare sphere, and for any point along either of these two paths, we form the state and measure the state. And here for the red path, we measure the real and imaginary parts of alpha. And we also measure the real and imaginary parts of beta. The solid line is the state that we know that we had formed. So this measurement procedure does a very, very good job of allowing us to measure the polarization state of the photon. So how did we do it? It's not so different from what Randy Hewlett did in that first experiment on weak values. We took a Gaussian laser beam, spatial filter, take a laser beam, make a very clean Gaussian from it, pass it through a quartz plate. The quartz plate displaces the horizontal from the vertical. A distinction here. A strong measurement would be one in which the two components are entirely separated from one another. A weak measurement is one where they are not entirely separated from one another. Because they are not totally separated, once you project them back into the same polarization state, they interfere with one another. So you can think of this as a form of interference. And then you make the strong measurement by projecting into the diagonal or the anti-diagonal polarization state. So that's how we did it. Now, in the same group of people, Jeff Lundeen and Charlie Bamber, in a later publication that same year, point out that you can actually measure the full density matrix using this. So in our first demonstration, we had measured the polarization state of a pure quantum mechanical state. But you can, this same trick works for measuring mixed states as well. So in our same paper here, we measured the density matrix. In fact, this is still the density matrix of a pure state. We still haven't done the density matrix of a mixed state, but that's pretty much the next step along the line in what we're doing. So let's see. You see, for left-handed circularly polarized light, you need both a real and imaginary part to the density matrix to show that the x and y are shifted with one another by 90 degrees, whereas for horizontal polarization in a horizontal vertical basis, you just get one peak here, and we chose arbitrarily to have our phase convention so that it was purely real and not imaginary. So things like this tend to get publicity. So especially in Canada, so the National Post, this roughly speaking is like USA Today. Only bad thing you can say is that they put the student's name and not my name at all, but maybe he deserved it. Maybe maybe better the other way around. Also, Science Recorder says that scientists discover a way around Heisenberg's uncertainty principle. I think that's perhaps a slightly too strong a statement for what we claim to have done, but we'll take credit if people think that's what we did. Okay, so the next thing I want to tell you about is that we've measured the state vector of a state embedded in a 27-dimensional Hilbert space. And we feel this is significant because, one would expect direct measurement to become increasingly useful with the size of the Hilbert space. You can't really, tomography might be very, very difficult in terms of the huge amount of data So if you can make a direct measurement, that could be useful. Sasha, is that?
Before you move on, just to understand how you did it for a single qubit. So you need probably like 4 outputs. If you have 2 complex numbers, you want to have 4 real outputs. I didn't understand in your experiment what were these 4 channels.
You cannot do it on a single photon. The whole idea of weak measurement, I'm not sure this is what you're saying, but let me say it for everyone. You have to repeat the measurement. You have to repeat the measurement many, many times. The whole idea is that you're extracting only a small amount of information for each measurement.
Yes.
So you have to repeat it. But your question was what are
since you directly measure the wave function, as I understood, you are directly measuring like 4 numbers, or at least 3 numbers. So in your apparatus, what are these 3 numbers?
Yeah, let's go back and try to figure it out together.
Yes, in your setup.
Let's see. So experiment 1 was for the wave function. Experimental 2 was for the Dirac distribution, which is an alternative to the density matrix. So the here.
So probably these are intensity of these 4 dots?
It's the intensity of the 4 dots.
Okay, intensity of 4 dots. Okay, very good. Okay, good. So then this is the answer.
Yes. They've moved apart from one another.
Okay, good. Intensity of 4 dots. Good.
Okay, so why 27-dimensional? What do we know about the English language that has 26 of them? Okay, so I am working on quantum key distribution. So this is the motivation. So this is the motivation. I am trying to work on quantum key distribution, but impressing many more than 1 bit of information per photon. So the Laguerre-Gauss modes of the radiation field are in principle an infinite dimensional Hilbert space. So we are trying to build a QKD system in which we can encode 3.5 or 4 bits of information onto each photon. So then the question is, if you succeeded in doing this, you need a diagnostic to tell yourself exactly what was the state of the photon if the photon is embedded into this Hilbert space. It would take us too far apart, too far off the topic, but these are the Laguerre-Gauss modes. You recall that to do quantum key distribution, you need a mutually unbiased basis. So this linear combination of these Laguerre-Gauss modes is unbiased with respect to this set. So that's what this is up to. We are trying to build a quantum key distribution system that will carry many bits of information per photon. If we form some arbitrary linear combination of these, how in the world would we go out and measure the state vector in that situation? So here's how we do it. Helium-ion laser, for now, very, very highly attenuated, so that we have at most 1 photon within the interaction region at a given time. A spatial light modulator impresses any Laguerre-Gauss mode or any linear combination of Laguerre-Gauss modes onto this. Okay, so we form the state, and now we want to analyze the state. This is a strange and wonderful device invented by Miles Paget. It will take in quantum key distribution, you have to make a measurement on only 1 photon. If you have a donut-shaped beam with a phase variation around the beam, how in the world would you make a measurement of the phase variation making only 1 measurement? Miles figured out that there is a certain there's a certain lens that is so terribly bad, it has so much astigmatism that the image of a donut is a hot dog, to use a culinary language. Now, if you have a phase variation along a hot dog, that's just a wavefront tilt. So all you do is you put a lens there, and then different plane wave components come to a focus in different points. So that's how we do it. So here, then as a technical point, if you coherently make 3 copies of this next to one another, the diffraction limit becomes 3 times smaller. So you get very, very high distinguishability among these. So that is how you make, and then you send it to a spatial light modulator. This spatial light modulator is not used as a spatial light modulator. You stop and you think, how does a spatial light modulator work? What you're really doing is you are changing the polarization of the light. So we are using a spatial light modulator to perform the weak measurement on a beam of light. And then we make the strong measurement by going into the Fourier transform plane and making a strong measurement on the polarization. And then we read this out into the 2 orthogonal polarization components. So here are the first set of results. So here's what we do. We take a pie-shaped opening in a screen, and we just let light get transmitted through this opening. By the uncertainty relations, if you have a small angular range, you have a large range of orbital angular momentum values. So we've made the measurement of the state vector of the light that is transmitted through this opening. But then you ask yourself, how do we know that we did it correctly? Any idiot, so to speak, can measure a probability. What's the issue of quantum mechanics is to get the probability amplitude. So this is what we did. Oh, it's terrible. There's a slide missing. But what we did, I'll just tell you in words. This opening here, this pie-shaped wedge, we rotated it this way, and then we rotated it this way. And we find that we get the same probability density function, but that the phase has a different slope, depending on which phase we do. So I guess in putting this talk together, I lost one slide. And now let me get to the very last part of the talk. And this is amplification of angular rotations using weak measurements. This appeared in Physical Review Letters in May 2014. People had, like John Howell, had used weak values to make very careful measurements of angular displacements or of translations. What we want to ask is, if you have a very small rotation, can you measure that? Well, of course, if the system is connected to a goniometer, it's very easy. But let's say that your optical component is out in space and you don't have a reference frame that you can reference it to. So I want to know if some optical component has been twisted around its axis by a small amount. So here's some introductory material, which I will just we'll start in here. So there are many situations which you would want to make a very careful measurement of a rotation. And a number of techniques have been proposed for doing so. Some of these are quantum metrology based. Our feeling was that if we can do this with weak measurement, this might be a very much simpler way of making highly accurate measurements of rotations. So, in words, the weak measurement for sensitive estimation of angular rotations is based on the concept of weak value amplification. The shift of the state of a pointer in both angular position and conjugate orbital angular momentum bases is used to estimate angular rotations. This is done by an amplification of both the real and imaginary parts of the weak value of a polarization operator that has been coupled to the pointer, which is a spatial mode via spin-orbit coupling. Same theme over again, right? All of these are a variation of the same basic thought, but with different laboratory applications, which could be very important because for different circumstances, you might want to make a different measurement. So I guess here all we point out is that the angular position and the orbital angular momentum spectrum are Fourier conjugate pairs. So if I said this before, if you restrict the azimuth through which light can be transmitted through a screen, that will open up the spectrum. If this is wide open, you can have this with just a single value of OAM. But if you have a very narrow slit in angular space, you necessarily have to have a broad set of range of orbital angular momentum. So here are just some examples. A beam that does not have any orbital angular momentum could, for example, be a Gaussian beam. A beam that carries 1 unit of angular momentum will have a 2 pi phase variation as you move around the beam. A beam that carries 2 units of angular momentum in units of h bar will have a 4 pi phase slippage as you move around the beam. So how do we actually do this in the laboratory? Well, we write a computer-generated hologram onto a spatial light modulator. We diffract a Gaussian laser beam off of the spatial light modulator. The diffracted light will come out in a mode that carries orbital angular momentum. So the first order mode would have +1 units. The -1 diffracted order would have -1 units of orbital angular momentum. Now, how do you measure the orbital angular momentum of a beam of light? Let's say you have a beam of light of this sort here. How do you make the measurement? Well, you can do this backwards. Here's your beam of light. You send it on to the conjugate of this hologram, which we show here just by flipping it top to bottom. When this structured beam diffracts off this hologram, it turns into a TEM00, or a Gaussian laser beam. You then try to couple it into a single-mode optical fiber. Only a single-mode field can couple into a single-mode optical fiber. So you put a detector here. If the detector goes click, that tells you that the beam of light here had an OAM value which was equal and opposite to the OAM value of the hologram that you would put here. So that's how we do the experiment. Okay, so our pointer then is this pi-shaped wedge of light. The probe is the polarization of the beam of light. So the probe is a polarization qubit. The spatial part of the wave function, if you use that language, is a Gaussian in the azimuthal degree of freedom, and the state vector is the inner product of the two. So the weak interaction, and this is not so different from John Howell's work with Andrew. You have a Sagnac interferometer. You have one beam going around this way, one beam going around this way. The question is, if I take this Dove prism and rotate it by a very small angle, how small an angular rotation can I measure using weak value methods? So the interaction Hamiltonian is made up of two parts. One is the spin-orbit interaction, and that couples the spin of the photon with the spatial distribution. The other is the geometric Hamiltonian. This is the Berry's phase, or Panchratnam phase Hamiltonian. So after this initial state has interacted with this interaction Hamiltonian, the final state becomes this. So the spatial degree of freedom gets rotated one way and going through in the forward direction, the other way and going through in the backward direction. So here I just tell you what the two interaction Hamiltonians are. The spin-orbit interaction, well, delta phi over 2, that's the size of the effect. Sigma is the Pauli matrix, and L is the generator of rotations. So you can work that out. And now the geometrical phase interaction. So the Berry's phase that is acquired by a beam of light when it passes through a closed loop in parameter space is just equal to within a factor of 2 of the area on the surface of the Poincare sphere, something that Michael Berry worked out many, many years ago. So the trick here is just a trade-off between the spin-orbit interaction and this Berry's phase interaction. And then the post-selection process, well, depending on whether it's the real part of the weak value or the imaginary part of the weak value, you do it somewhat differently. The real part of the weak value is just the orientation of this pie-shaped wedge. The imaginary part of the weak value corresponds to the conjugate quantity, and the quantity conjugate to the azimuthal orientation is orbital angular momentum. So you can measure either or both of these quantities. Okay, so in the post-selection process then, okay, so here is our weak value of the Pauli matrix, and you see that it has both a real and an imaginary part. You can use either the real or the imaginary part to determine how far the Dove prism has been rotated. And here are the final results, or here are some of the final results. So the upper line is theory, lower line is experiment. So these are in good agreement with one another. Okay, so with no post-selection, you cannot even see that this pie-shaped wedge has been rotated. But with the weak value amplification, here a factor of 5, 8, 5.5, 8, with a minus sign. You can even see by eye that this has been rotated through a certain angle. You can also do it using the orbital angular momentum degree of freedom, but that's not what we show at this point here. So the significance here, I guess, is that perhaps not surprisingly, once you understand how weak value amplification works, that it can work for any set of degrees of freedom of a physical system. On the other hand, if you think that this is important, you want to be able to use it to measure whatever degree of freedom is of importance to you in a given context. And here is the here are the same results in orbital angular momentum space. So the blue is without the post-selection. This is just the orbital angular momentum values that came from restricting the size. The green shows that the OAM spectrum has been shifted, and this corresponds to the imaginary part of the imaginary part of the weak value. So the conclusions here is that we've shown that we can use weak value amplification in the context of the azimuthal degree of freedom. The shift in angular position is related to the real part of the weak value. The OAM spectrum is shifted by a way that depends upon the imaginary part of the weak value. And again, this is just another example of how weak values can be used to perform measurements of importance to metrology. Again, since I was not backing off on controversial issues, I believe that, maybe this is not controversial at all, I believe there's nothing quantum mechanical about this. Everything that I've said here lends itself to a purely classical interpretation. But still, it's actually a lot easier to understand what's going on when you take this and express it in a quantum mechanical language than to try to figure out exactly what is going on with this horribly complicated polarization optics. So, thank you very much.
Thank you so much for the beautiful talk and the beautiful experimental result. And so you demonstrate that just the generations OAM is the Radial mode, and also the detection of the Radial mode is just the same specialized light modulator.
Yes.
Yeah. On that case, this is the exactly same hologram, or computational hologram of the SLM. In principle, yes. In practice, what is it?
So I was not very careful. We can work in a space of Laguerre-Gauss modes, or we can work in a space of pure vortex beams. When we say it's a Laguerre-Gauss mode, we're making a statement about the radial distribution. You can also have a beam of light with an entirely uniform distribution in the radial degree of freedom, and the azimuthal, and only an azimuthally varying phase. In our work, we go back and forth between pure vortex beams and Laguerre-Gauss beams, depending upon which situation we are more interested in. A Laguerre-Gauss beam and a pure vortex beam have exactly the same azimuthal phase structure.
Right.
So you can form it with one and read it out with the other with no problem. What differs is the radial distribution.
I see. And also,
and I'm still struggling with this. I'm still struggling with this myself.
Mm-hmm.
Here's what I believe. if you want to encode in both the radial degree of freedom and in the azimuthal degree of freedom, then you want to use the Laguerre-Gauss modes. Of course, there's this theorem. I'm not a theorist. Infinity times infinity is only infinity.
Yeah.
So since the azimuthal modes are already infinite in number, maybe you are making your life more difficult to encode both in the radial degree of freedom and in the azimuthal degree of freedom.
Yeah.
On the other hand, from practical points of view, maybe you do not have enough pixels in your hologram or your spatial-like modulator.
Yeah.
You could go to an OAM value of 1 million.
Right.
So maybe you would be much, I don't know, let's be realistic, 10,000. Maybe you'd be much happier going to an OAM value of 100 and a radial index of 100.
Right.
Which is pushing the state of the art, but is realistic.
Yeah.
Whereas getting all of your encoding in the azimuthal degree of freedom would not be realistic.
Yeah, on that case, on the increase on the azimuthal index is L, is the increase. On that case, did you consider the effect of just a GUI phase?
Yes?
Yeah, such kind of that, this is the phase.
No.
This is a
we know of the GUI phase. And
Yeah.
and depending on how you do the experiment, it shows up in either a trivial way or in a non-trivial way.
Yeah.
So it's something we worry about.
All right.
It keeps me asleep. It keeps me awake at night.
Okay, right.
Or I just get so tired I just fall asleep at night.
Yeah, it's okay.
Yeah.
Thanks.
So the GUI phase forces different OAM values to interfere differently in the far field.
Yeah. Then this to interfere or just in the last slide, last talk is you demonstrated the angular rotational amplification program. On that case, it seemed to be such kind of the interfere. You use as just the interfere. It's the pure Laguerre-Gauss, and also pure non-Laguerre-Gauss mode.
I love giving talks because
Yeah.
I get challenged by the audience.
Yeah, I'm so
I
sorry.
go home and think.
Yeah.
But here's what I think. These were basically collimated beams of light. It's when you bring them to a focus that the different modes will suffer different GUI phases.
Yeah.
If you're basically collimated, you don't really have to worry about the fact that different modes suffer a different phase.
All right. Thanks.
I was curious, with your 27-dimensional space, you talked
One's
about...
for spacebar, of course.
Yes.
26 letters of the alphabet and spacebar.
Of course.
Okay, but continue.
You mentioned you did the direct measurement,
Yes.
and this is a high-dimensional space, so presumably this is a huge improvement in post-processing, something like that.
Yes.
Do you have any numbers for a comparison to traditional tomography?
Not an instant recall. When I first went to Ottawa, I started working on tomography. And then I told my students, hey, you are competing against yourselves. You spent your first 2 years doing tomography, then you realize that tomography is a really bad idea, and now you're doing it this other way. I need to get this straight. And don't let me forget. Don't let me forget. I want to answer the question not only for you, but for me.
So, Bob, somehow I missed this most recent paper of yours about the rotation. I wanted to ask a question.
Yes.
When you tilt your Dove prism, if I remember, I think your friend Miles Padgett has written some papers about how this changes the polarization of the beam. How does the polarization beam of the Dove prism affect the interference physics in your interferometer?
I forget. Oh. No, you're certainly right that the Fresnel coefficients are different for right. I love giving talks because the audience challenges me to understand things that I thought I understood but don't. With Justin, I can pretend that I forgot. Since I see you once a week, I can't forget. So let me think about that. Yeah. Maybe it's not a very big effect. I mean, the Fresnel coefficient. So the Fresnel coefficient is going to be slightly different for slightly different orientations, and maybe that was not a crucial part of the measurement that I need to think. Thank you.